Hey guys, so let's discuss a new designing question today, which is design AI powered Kafka, okay, which will be a next gen streaming system. So what is next gen here? Next gen is future ready, okay, future ready, smarter, more automated streaming architecture compared to traditional systems. Okay, so we will see the traditional Kafka, and plus on top of that we will see the AI feature. We will apply AI feature on that. So the problem statement is you need to design a smart Kafka like system that handle real-time events like millions per second events. Okay, so events in the sense, when you're watching Netflix, let's say, and you're playing the your series, you're pausing the series. Okay, so this play, pause, everything will create one event. Okay, we'll send that event to Kafka. If you are getting network issue, so your series is buffering, so that also will get stream as an event to Kafka cluster. Now, use AI to optimize partitioning, routing, scaling, consumer performance, and failure prediction. We know that in Kafka architecture, you will have one consumer, you will have one broker, and then you will have a producer, broker, and then consumer. Okay, so producer will produce events on this broker, and then consumer will consume event from this broker. This broker will divide it into multiple chunks, like topics, you can say. Okay, so this is topic 1, topic 2, like that you will have a multiple topics, and then inside topic you will have a multiple partitions as well. Okay, now these partitions are divided into the blocks. You can say that blocks as offset. So that offset you will determine, using that offset you determine that till where this consumer has read the data and all these things, so that if you need to replay this event again, or you need to, if this consumer goes down, then another consumer from the offset, from where this consumer one has left. Now, so this partition routing, so now you can have a multiple partitions, okay, multiple topics, you can have multiple brokers as well. Okay, so that if one broker goes down, consumer producer can produce event in another broker, and consumer can consume events from there. So to which route, to which broker we need to route the events, so that that comes under this routing, and then scaling. So you can scale, you can create multiple brokers, and consumer performance. Okay, how consumer is performing, whether there is a consumer lag or not, because producer is producing the events but consumer is slow, let's say. Okay, so we need to check that consumer lag as well. So consumer performance and failure prediction, if anything failed. Okay, so in so earlier only you will come to know, okay, this one is gonna fail, so we can have the alternative for that. So for example, your system can handle 5 million plus events per second. Okay, and with less than 50 millisecond latency, 10,000 partitions, and 500 brokers. Now, traditional Kafka design, you can, so whatever I just explained, it's here that you will have topic, partition, producer, broker, okay, replication, consumer group, and then offset management. So consumer group, here you can have either single consumers, or you can have a consumer group, okay, CG, where you will have a multiple consumers. But the rule here is that, let's say you are reading from this partition. Okay, so if there's individual consumers, they can read from same partition. But if they are into a group, then from group, one consumer can read from one partition. Okay, it's not the case like from one partition two consumers are reading from the same group, no. But yeah, this partition can be read by this second consumer, and then first partition is read by first consumer. So that could be a case. Now, we have seen this real world example. If we see, so we will see the real world example for Netflix and Amazon. Okay, so now let's talk about Netflix first. How Netflix uses event streaming. See, Netflix generate billions of events daily. Okay, billions of events. So events generated like play, pause, stop. Okay, you're playing your video, you're pausing your video, you're stopping your video. Search queries, you're searching something, and then recommendation clicks, you're getting recommendations on your home page that you can watch this one also. Buffering events, okay, you're getting buffering, so this one also will get there, and it will check. and device type, from which device you are watching the movie, from mobile, from laptop, and all these things. Okay, so these all things will come under events. Now use cases, if you talk about, so real-time recommendations like user watch money heist, okay, and event streamed instantly, AI updates recommendations. So user is watching money heist, so AI will update the recommendation, and then he will recommend me a similar kind of series. So this is the pipeline, like user will take action, either view, add to cart, click, like, and then the event will go to Kafka cluster, and then from there ML pipeline will run. Okay, so feature extraction, feature store thing will be here. Feature ML pipeline I have already explained in my one design video, so please go and watch that from the series. Okay, and then this feature store will go and will be used by ML model, okay, to train himself, and then he will uh, he will update the recommendation API, and then recommendation API will give you a recommendations. Now query monitoring. Okay, second is query monitoring. So we are talking about use cases. So first one is real-time recommendation, second one is query monitoring. Detect a buffering spike in region, trigger alerts. Okay, so if let's say you are getting buffering, and let's say other people from the same region is also getting buffering, so it will see that okay, in this region buffering spikes is there, right? It means that some problem is there, and it will trigger the alert that some problem is there, please check there. Because let's see, Netflix is using by entire globe, and globe is divided into the regions. Okay, and your application is deployed in per region, let's say. So region wise it will detect it. Now personalization, so it will track your watch time and your genre preferences, and using that it will recommend you the movies or series where AI fits here. So predict trending content, pre-warm caches, and allocate partition dynamically. Okay, so now here AI will in advance only he will predict what content will be trending. Okay, and then pre-warm caches, so it will in a cache it will load that content, okay, earlier on the before the traffic spikes, and then allocate partitions dynamically. So here is the diagram you can see. Let's say new show release. Okay, so AI will predict, okay, there will be a traffic spike. So what he will do, in advance he will scale partition. Okay, he will create a multiple brokers, he will create a copy of a partition, he will create new partitions, and then when the spikes came, okay, so it will handle that spike. Okay, and when the traffic arrives, so it will handle that spikes, and then your system will be stable and smooth with no backlog, no lag, or the consumer will be happy, users will be happy. Now real-time example of Amazon. So in Amazon, even Amazon is even more event heavy. Okay, so what all events it will capture? So something like product click. Okay, you clicked on some product, you search something in Amazon search bar, you add something to your cart. Okay, you purchase something, your payment status, either it is successful or failed, then your delivery tracking, all these events will get generated, okay, and go into the Kafka streaming engine. Now use cases, if you see here, click stream analysis. Okay, so track every user interaction used for recommendation and UI optimization. If you are clicking anything, it will recommend you product according to that, and will show product on your UI screen also. Fraud detection, so detect abnormal patterns like rapid purchase, someone is purchasing something, okay, rapidly, and multiple cards. So here we will use AI plus streaming. So events like login attempt, transaction, payment, account, and account updates, this one are the events will go to Kafka streaming platform. Okay, and then it will go from there, it will go to ML model. ML model will train himself, and then he will in real time inference. Okay, means real time he will take action, he will calculate the risk score. If risk score is let's say 0.7 is greater than 0.7, then it comes into the high risk category, so he will block that request, or he will allow if it is lesser. Okay, so that kind of thing we do here. Now real-time inventory, so update stock instantly after purchase. Order processing, so like user has means he has created one order, okay, and then your payment service will be there for the payment authorization. After that, inventory, he will update the inventory, shipping, okay, delivery related things, and then notification. So all this processing pipeline is also handled by him. Now where AI fits here? So demand prediction, okay, AI forecasts which product users will buy soon based on past behavior or the trends. Dynamic pricing, AI adjusts product prices in real time based on demand, competition, and user behavior, okay. And then traffic surge prediction. So like you have a prime day sale, okay, or annual sale of Amazon, so that time he knows that okay, traffic will spike here, traffic spike will be here. So AI predicts upcoming spikes in user activity, so system can scale before load increases, okay. He will add more servers and all. Why add AI to Kafka? So now, traditional Kafka, we were using static partitioning, okay, manual scaling, and fixed config. But here the problem was hot partitioning and consumer lag. Okay, hot partitioning means from one partition only, all load is coming to one partition, okay, and then consumer lag is also there. So like consumer speed is slow, okay, but producer speed is fast. So in that case, these were the problems, and now AI solved dynamic optimization, okay, and then predictive scaling and intelligent routing. So if you talk about here feature like partitioning, so it was static in traditional, but AI Kafka it is dynamic. Scaling was manual in traditional but predictive in AI Kafka. Routing was traditional hash based routing, okay. In traditional it was hash based routing, but in Kafka, AI Kafka, it is ML based routing. Now lag handling, if you say, so in traditional it was manual, now it is auto. So that's why we are using AI Kafka here. Now high level architecture, if you see, here you can see that you will have one producer, and that can be anything like app, your service, your IoT, okay, Internet of Things. So that will produce the events, and AI routing layer will do the dynamic partitioning, okay, hotspot avoidance, and then priority assignments. Then you will have an AI cluster where you will have brokers partitions, okay, so multiple brokers, it will route the traffic accordingly. And then AI consumer manager, so what he will do, so that will check the lag detection, auto scaling if it is required, and then smart assignment, okay, to the consumer. So now consumer will have ML analytics or API. Now here he will send the this data to downstream services, that could be your recommendation engine, fraud detection, or caching, okay. So this is how the architecture looks like with AI. Now what each layer does, okay, producer generate events, AI routing layer decide best partition dynamically, Kafka cluster stores and replicate events, AI consumer manager optimize consumer performance, consumers process events, and downstream services recommendation, fraud detection, etc. These are the downstream services which will use that events. Now where AI exists, okay, so AI routing layer, here we will use AI routing layer, AI consumer manager, predictive scaling, and failure detection. Where AI fits, so AI based partitioning, okay, hot partition fix, some partition overloaded, so all traffic for one product goes to same partition, so there you can use AI. So what AI solution will be, so model predict load, okay, model predicts load, dynamically route messages. He will predict, means in advance only he will predict that okay, this partition will get more load, so he will route that earlier. Instead of finding the partition like hash based, okay, now he will use the ML model for that which will get the event feature, and here event feature would be like user ID, traffic pattern, time of the day, and then event type. Now intelligent load balancing, okay, so what is intelligent load balancing? AI predicts which broker is overloaded and which is underutilized, so route traffic accordingly. Predictive auto scaling, so AI forecast traffic spikes, so for example sale on Amazon, so AI predicts a spike, adds broker before traffic hits, okay. Now consumer lag optimization, some consumers are slow, so there would be a lag. What would be the AI solution for that? Detect lag pattern, auto scale consumers, and reassign partitions. So means just increase the consumers, right? So then from where it is reading that data, so just reassign the partitions to those consumers. Failure prediction. So this is very powerful. AI predicts disk failure or network latency anomalies. So how he will prevent it? What it will prevent? Broker crashes and data losses. Now smart retention policy. So what is that? Instead of fixed retention policy, AI decide keep important data longer and delete low value data earlier. Priority based streaming, if we talk about, so let's say if you have a event payment, so its a priority will be higher, and then if you have a click, then it would be medium, and for logs it would be lower. So ensure critical events processed first. End-to-end flow, if you check, so it would be like user watches movie, event generated, AI routing layer, what it will do, choose the best partition and avoid hotspot. Then broker, what it will do is store events and replicates it. AI consumer layer, what it will do, it will assign fast consumers and prioritize important events like play and pause. User has just paused it, so that will be the important one, right? It should pause it that time only. And like writing log could be, the priority would be later. Okay, now AI model used. So for partitioning we are using classification model, for load prediction we are using time series forecasting. Okay, and then for scaling we are using regression, failure detection we are using anomaly detection, and for ranking events we are using ranking models. Now trade-offs, if you talk about here, so AI routing, see, better load balancing but adds latency, that is for sure, right? Then prediction error, so proactive scaling but risk of wrong decision. If he has predicted and he has scaled, he has added some servers, but what if it was the wrong prediction, then you have to bear the cost. Then complexity, so smarter system but harder debugging. And cost, so automation but more infrastructure. So challenges, if we talk about here, wrong prediction, that is we saw. Okay, so fall back to static Kafka logic, so that will be the solution. Okay, you will also always have a default Kafka logic, so we will go with that. Latency increases, so cache AI decisions. And model drift, let's say user behavior has been changed, so in that case what is the solution? Continuous retraining. Okay, again retrain the model. Hybrid design, if you talk about, so do not fully replace Kafka logic. Instead, see, I told you that we will use the default Kafka also here. See, if AI confidence is greater than your threshold, so use AI decision, otherwise go with default Kafka logic. Now real world inspiration, if we talk about, so concepts we use, so in Uber they are using dynamic event routing, okay, using the AI. LinkedIn, they are using Kafka plus ML pipeline, and Netflix predictive scaling. Okay, so we can say AI enhanced Kafka extend traditional partition log design by adding machine learning for dynamic partitioning, predictive scaling, intelligent routing, and failure detection, improving efficiency and reducing hotspot in large scale streaming systems. So that's it. Thank you.